I was a program manager at DARPA. I started the PAML program, and I also started the HACMS program. And I'm going to be talking now about the HACMS program. The idea of HACMS is to use formal methods to eliminate exploitable bugs in software, so to improve the security of cyber-physical kinds of systems using formal reasoning kinds of techniques. So we didn't have anything to do with machine learning per se, but I think as you look at the kind of system and architecture of cyber-physical systems, like Jeanette was just pointing out, you can see lots of places where we could slot in or need to slot in artificial intelligence, machine learning kinds of approaches, and then we need to be able to extend the formal methods framework that I'm going to talk about now to be able to handle those kinds of new technologies, or learning and adoption kinds of technologies. So this, you can think of this as kind of a baseline of what's the current state of the art of using formal methods to build systems that are as secure against cyber attacks as we know how to make them. Sorry for the jerky animation. Right, so as you're probably aware, right, network computers are really unacceptably insecure these days. Everything from desktop computers to SCADA systems that control nuclear power plants and uranium enrichment facilities and sewer treatment plants, to medical devices like insulin pumps and pacemakers, to communication devices, computer peripherals, and various kinds of vehicles, like, for example, this Jeep that ended up in a ditch last summer as a result of hacking and caused a recall of over 600,000 Jeep Cherokees. So why is this so easy? Why are hackers able to take control of pretty much any kinds of Internet of Things device you want to think about? Well, the problem of security is super hard. If you want to build a system that's secure, you have to solve so many different problems at the same time. For the purposes of this talk, I'm just going to talk about implementation errors and how we can use formal methods to dramatically reduce the implementation errors in systems and therefore dramatically increase the security of the resulting system. Right, so focusing just on implementation errors, though, is a good choice because implementation errors have lots of pernicious effects. So this data from the IBM 2012 Task Force report shows sort of the number of vulnerabilities reported over time, which not surprisingly they're going up. Somewhat surprising that they're kind of low in total numbers. But the really interesting thing is that in 2012, 3,400 of these vulnerabilities had public exploits available. So a vulnerability is just a bug in a system, not that big of a deal. An exploit is something that an attacker can actually leverage to take over control or in some way corrupt your system. So exploits are really, really bad. And 42% of the published vulnerabilities actually had public exploits available. So that's bad. What can you do with an exploit? Well, an attacker can use an exploit to achieve remote code execution, which means that they can execute whatever code they want on your computer, making your computer do whatever they want. So the Microsoft Security Bulletin MS-15078 last summer revealed a bug in the Adobe Type Manager library on Windows that was allowed remote code execution on every single Windows platform that was supported that summer. So basically, if you had a Windows machine, you had this vulnerability on your system. Heartbleed similarly allowed attackers to exfiltrate information, basically steal information off of your computer in a way that left no trace, so you couldn't tell whether your system had been attacked with this mechanism or not. So exploits can take over control and can exfiltrate information. So actually changing vulnerabilities into exploits is really hard. It requires a lot of very specialized skills that most people don't have. Even most trained computer scientists don't have this capability. But entrepreneurial black hat hackers have been able to convert vulnerabilities to exploits and then package up those exploits into exploit kits that they sell on the black market, which means now all you have to do is be able to go to the black market and buy an exploit kit, and now you can use it to exfiltrate information or take over computers. So this is a big problem. This is why DARPA is really interested in this kind of these kinds of problems. So the hypothesis behind the HACMS program is that we could use formal methods-based approaches, mathematical techniques to producing software, to dramatically decrease the vulnerability of Internet of Things kinds of devices. Now, if you've been around computer science for very long, you might have the reaction like, yeah, I've been there. I tried that. Didn't work. Why are you bothering with me with this again? And I think there are actually a number of different reasons of why now is a really good time to re-examine this hypothesis that formal methods could help us build better software. So what are those 4 reasons? One of them actually has nothing whatsoever to do with the formal methods community. It's just that the hardware architects have been amazing and have produced orders of magnitude improvement in both cycle speed and memory sizes. It turns out most formal methods are very elaborate search procedures, very labor intensive, time intensive. And so just by having faster computers and more memory, we get a big leg up. A second huge advantage is increased automation. So we heard Tom talk earlier today about SAT solvers It turns out SAT solvers can be used to encode very complicated questions about software using enormous formulae, and then we can then throw those questions over to these automatic SAT solvers that can solve them automatically. And on top of that, we can build SMT solvers, which add theories of arrays and integers so that we can ask more and more complicated questions about our software that systems can solve automatically. So basically, computers can do more of the work of formal verification rather than PhDs in verification. So that's a second reason. Then the third reason is back in the old days when formal methods researchers were first trying to do this, they had to simultaneously invent the formal method technique that they were trying to use, build a tool to embody it, and then apply that technique to the system that they were trying to assure. And that was like too many jobs for one person to do or one research group to do at a time. The situation today is really, really very different because lots of groups have built fairly robust, fairly solid software that's now available on the web for anybody to be able to download and use. There's reasonably good documentation. Books are starting to come out on how to use these systems. So now when you want to use formal methods techniques, you don't have to invent the formal methods tool to get started. You can go and use formal methods tools that many other really, really smart people have already created for you. And I would say to add to those kind of three technical reasons, there's a sociological reason as well, which I think that we're getting to the point where developers of certain kinds of software know that the complexity of what they're trying to do is beyond what they can actually do without having more elaborate tools to help them. So an example of this insight comes from Amazon Web Services, where they've started using TLA and model checking to debug their designs, because in the words of the people who wrote the report, when you have a 1 in a million event is something that humans are really, really bad at reasoning about, right? We have terrible intuition about 1 in a million events. As far as we're concerned, that never is going to happen. But in Amazon Web Services, 1 in a million events happen every second, right? So that's a case they actually have to worry about. And the formal methods tools help drive them into those cases. And they're willing to accept that and acknowledge that. Okay, so DARPA's HackOps program was designed to test this hypothesis. So the setup was, the hypothesis was, as I said, formal methods can allow us to build vehicles that are less susceptible to cyber attack. The threat model was no physical access. The attackers had to be able to break into the system without physically touching the device. That's not to say that attackers can't break in if they have physical access. If they have physical access, it's easier to break in. But remote attacks scale much better, right? You can launch a remote attack against thousands of systems across the world simultaneously, and you can't do that with a physical attack. It's much more labor intensive. So they're kind of more of an important threat according to DARPA. We assumed the hardware was correct. We know that's a terrible assumption, but you have to start somewhere. And we started with the various experimental platforms. So we had various teams. The AIR team is what I'm going to talk about today for the interest of time. The AIR team had an open source quadcopter that you could buy from Amazon. The idea behind this platform was that all of the researchers on the program could have complete access to the system and know absolutely everything about it. Then Boeing supplied the unmanned Little Bird, which is a proprietary helicopter with ITAR restrictions. Basically, only Boeing engineers could see and work on this platform. The idea was that the whole program would work on, the whole team would work on the tools and techniques on the quadcopter, and then the ideas would be transferred over to the helicopter by the Boeing experts. So at the start of the program, we had a professional red team conduct penetration testing exercises against all of the program vehicles to see what was the security of the systems we were starting out with. They had 6 weeks of full access to all the source code, everything they could find out about the vehicles. And at the end of that time, they were able to compromise all of the vehicles they looked at. It really wasn't difficult. I'm not going to show you this video. The link to the slides has more slides than this and actually has the video. You can see the blue team researchers breaking into the quadcopter using very little expertise. It's actually very, very easy to break into a quadcopter. It's designed to be connected to easily. It's not designed to be hard to break into. So this slide shows a schematic of what the researchers on the AIR team did. They started with the off-the-shelf quadcopter that had a monolithic software stack. It had no real-time operating system. It had no security whatsoever. This is why the red team was able to break in so easily. They then refactored it. They replaced the underlying hardware with a slightly more powerful chip. They put in a RTOS, real-time operating system layer. They added a hardware abstraction layer, so the code above didn't know if it was running on this platform or the original platform, which they then released open source and won an award for that contributions to the Arducopter community. They then had the remaining quadcopter software, which they then started to replace these pieces with high assurance software. So they replaced the RTOS with a high assurance version that was developed by Data61 in Australia. And they rewrote the flight control code in a domain-specific language in Haskell that would be guaranteed to be memory safe and not have the kind of overflow errors that hackers like to use to break into systems. And then from the, they also had a DSL that described the overall architecture of the system, which then went up into a system-wide tool that Rockwell Collins developed to be able to reason about system-wide properties. And then from that, they generated the glue code that connected all these pieces together. So at the end of phase 1, we had this much of the quadcopter, about 80% of it had been replaced with high assurance software. That was then handed off to the red team again at the end of 16 months. So the red team assessed how much of the functionality of the original quadcopter had been replicated in the new high assurance copter. About 80% of the functionality was there. Everything from stability control, altitude hold, directional hold. They added a denial of service detection capability, which responds in a mission-specific way. And most of the GPS waypoint navigation was implemented, but not all of it. The air team used that high-level model to prove system-wide properties about the system. They proved that the system was memory safe, so there were no buffer overflows, there were no buffer underflows, because if either of those existed, the system would not be memory safe. They proved that the system ignored all malformed messages. They proved that they ignored all unauthenticated messages. So it was much harder for the red team to pretend to be a legitimate user because you would have to have authentication credentials. They also proved a liveness property. They proved that all good messages that were actually received by the quadcopter would eventually be acted upon. The red team also, they found they had full access to the system, all the source code. They were able to participate in all the design meetings. They were able to ask questions of the design team, so they knew as much as you could possibly know about the system. And in 6 weeks, they were not able to break into the system or disrupt its operations in any way, which my colleague at DARPA, who's a penetration testing expert, his assessment is that that quadcopter is the most secure UAV on the entire planet, which is a little scary if you think about what UAVs do. Right, so that was the end of phase 1. So HACMS is now in the middle of phase 3. So the question is, well, what happened in phase 2? In phase 2, the air team took the quadcopter and they modified its architecture to match the architecture of the unmanned Little Bird. It now has 2 processors instead of 1. The one processor is the flight control computer that more or less mirrors the functionality of the original phase 1 machine. And the second one is the mission control computer that controls things like the communication to the ground station and fly to this location, then fly to that location, take this picture, fly to this other location. That's the mission control computer. They ran SCL4 on the mission control computer. They ran the RTOS on the flight control computer. And they had that same architecture on both the quadcopter, which they call the SMACM copter, and the unmanned Little Bird. At the end, they were able to do a flight test of the unmanned Little Bird 18 months earlier than they expected to be able to do. So the test pilot flew the high assurance code. The high assurance researchers were like, oh my God, that's like our code running on a real helicopter with a pilot in the air, and everything went good, right? The pilot couldn't tell that he was running high assurance software instead of the original software, which is exactly what you want. Then to test the security properties, the air team allowed the red team to put whatever code they wanted in a partition on the mission control computer. They used the SCL4 microkernel to control to set up that partition. And the red team had, again, 6 weeks to try to break out of that partition, and they couldn't do it. They couldn't break out. They couldn't disrupt the operation of the quadcopter in any way. So that's an amazing result that DARPA has been, the rest of the offices at DARPA have been like, wow, you can really do this with real systems. Okay, so that's the result of HACMS. So lots of different kinds of system software has been able to be verified to be fully functionally correct, like the RTOS or the microkernel that was used on the mission control computer. You're starting to see like every kind of software tool artifact that you'd like to be able to use to build robust systems is starting to be able to have a fully verified version available in the literature. So that's really exciting. There are a lot of impediments to using formal methods, right? It's not like every shop is going to run out and start using them right away. So some of these impediments are, there actually aren't that many people on the planet who are trained to use formal methods. Like in 2006, there were less than 5,000 on the whole planet. So that's one problem. Another problem is how much more effort it takes to produce the proof in addition to the actual code. Some of the times the overhead is really high. Other times it's down there in the feeling like, well, why don't we do that if they're going to get so much better security for only half a person year additional labor? Sometimes the performance is slower because often faster performance comes about because of fast paths. Fast paths means additional proof obligations. Formal methodists usually stop as soon as they get good enough performance, not best performance. Fitting into a development life cycle is really tricky. Facebook has some insights about how to do this. You have to make sure that the fine print is true. If your theorem, if you don't satisfy the assumptions, like your model of the underlying system is inaccurate, then your results don't apply. So where do we stand? So some of the lessons learned is don't try to verify existing code, write new code, because it's much easier to verify code as you're writing it rather than somebody else's code in the past. There are lots of challenges ongoing. One of the key challenges is how do you integrate with adaptive or machine learning based systems? Another key challenge is how do you handle concurrency? Many systems are much easier to prove if you don't have to deal with concurrency. And thank you very much for your attention.